So my name is Nicolas. I'm the CTO of IST Incorporated. Today I have half an hour to build with you an application that includes Post Quantum Cryptography, Zero Trust, PUF, and Root of Trust. So you might think this is madness, but it's just over there. So I'm going to go first to introduce what we do at IST. So we built a solution that provides root of trust for every electronic device that will be connected or that is already connected in the internet. So our core competencies, they rely in secure silicon IPs. Then we build security chips all the way to building modules, and we end up with a complete system integration with end-to-end solution from semiconductor all the way to integration with OT and IT. So I'm more Taiwanese than I look like. So I graduated from Jiaoda in Hsinchu. We established this company after research in the NYCU lab with a proof of concept in 2020. Then we got sponsored by Guokorwei and Jinjibu for 2 years to build this company. And we established in Hsinchu Science Park since the end of 2023. And we are ready to launch our product and PUF IC by the end of last year. Yeah. Okay. So first, if we want to understand what I do, we need to lay out the market context. Yeah. So we know we want to connect everything now. We have IoT. We want to put AI in coffee machine. We are afraid of quantum computers. So all of this is going to cause the landscape to evolve and is going to duplicate the problem. Yeah. So first problem is the quantum computing threat. So it threats the current key exchange algorithm. It can threat the critical infrastructure for telecommunication, for military, and it poses a national security implication. Next is AI. Thanks to AI, or not thanks to AI, we live in an hyper-connected world. So that duplicates the attack surface that will cause supply chain vulnerabilities. So that's the reason you see zero trust pretty much everywhere, because we need to integrate zero trust in our new architecture. We need to change the security perimeter. We need to systematically add identity-based access, role-based access, make sure we have continuous verification and monitoring. Okay. So I'm not the first one telling this. Traditional security is no longer enough. Software is no longer enough. So we need to build new system to answer this new challenge. So what we want to do is building IT and OT with post-quantum and zero trust. Okay? So what's the threat from post-quantum? The threat is modern key exchange. So the algorithm from RSA, ECC, and including also AES-128. So those algorithms that secure internet today, they are prone to be broken by quantum computers. So not everything is going to be broken. AES-256, SHA-256 is still considered safe. That's why you can see some company doing hybrid key exchange. But we know, and CEO Jason Lu explained it in Chinese before me, we need to migrate right now to post-quantum, and that includes the FIPS 203, 204. And that is especially critical if your device, if your manufacturing device that have 10 to 15 years life cycle. Because in 5 years, nobody's going to have a quantum computers, but in 15 years is not so sure. So if you have a device like a big server, a big router, or something that will last for a long time, you have to include PQC today. Yeah. So there are many candidates for PQC. There are many different algorithms that was proposed. So the whole point is to find a mathematical problem that cannot be solved by both traditional and quantum computers. So we have lattice-based, hash-based, and code-based cryptography. Obviously, lattice-based is winning. So right now we have Crystal, Kyber Dilithium, and Falcon. Very soon this year there'll be Sphinx as well. So in orange you see the one we can already use and implement in our device. In purple is the one that are not give up yet. They might be certified a little bit later, but we already know how to solve the post-quantum cryptography problem. Yeah. So let's take a look at why it's going to break the current internet. So when you want to build end-to-end communication between a sender and a receiver, you're going to have to exchange a secret, like a secret language. So in order to do that, we create key exchange algorithm. So both ends will create their own private key. That's your secret. Then you use an algorithm to derive a public key out of it. This is public, so you can share with public. Yeah. And then one of them will decide to select one big random number. And then the key exchange happens here. You're going to exchange a random number, like a seed, and you're going to exchange public key. So then on both ends, when you reassemble all the keys, you can get your brown key. That is your shared key. And that's how you build up an encrypted channel there. Okay? So why is it fine? Because a regular computer, the one you have at home, the one even you have in the company, it will take way too much time, way too much power to go back this way, to extract the private key from public key. But a quantum computer doesn't care. A quantum computer with enough qubits will be able to do it in a few hours. So if someone can access the private key from public key, and we don't have solution, it's probably the end of the world, even worse than Trump increasing the tax import here. So how do we solve this issue with current internet? It's not so complicated. We just replace the key exchange algorithm we've been using so far by the one that are proved from hacking from both traditional and quantum. So right now there are 3-4 algorithms that you can use and already integrate, and we need to start migrating now. This is the post-quantum part. Now we need to attack the zero trust part, because it's not because you have a post-quantum link that you have a zero trust architecture. So now we need to integrate this new concept of zero trust is never trust, always verify. So for those of you who works in zero trust architecture, you're going to recognize this NIST picture that we all try to understand when it came out. So the whole concept here is never trust, verify. You make sure every entity in your network has a least privilege access, and you have to secure every connection. So you're going to have those theoretical resources, so policy decision point, policy engine, policy administrator, and foreman, subject, and resource. So it's not so complicated to understand because we already, in our daily life, use zero trust architecture. So let's say you find a girl you like, you want to marry her. So you're the subject, and you want to access the resource. So the one who will decide to say yes or no is the enforcement point. That's the girl who will decide. But you have a mother-in-law to deal with, which is actually the one who makes the decision point. And the mother-in-law will check on you everything she can from social network, Facebook. She's going to access resource, probably use AI, make the decision, tell the daughter, marry him, not marry him. Typically, he works in a startup, not good. He doesn't have car, not good. He has a PhD, good. And then at the end, you have the policy enforcement point, and you can build your secure channel between subject and resource. Okay, so more seriously, I use a Microsoft reference, so everyone knows this tool, to explain more in detail what it implies to build in your company. So this is the zero trust approach from Microsoft. So you have here the device ID. You need to have multiple factor authentication to access the resource. And in the middle, you have the decision point, you have the enforcement point, which is Azure Directory and Microsoft Intune. So you have like this ecosystem for you to do secure channel authentication and device identification. So that means you're gonna need a user login, user password, and UID. You're gonna need to set up multiple factor authentication, and complement of Microsoft is gonna cost you $10 per month to have Microsoft Intune. Then you're gonna have to manage admin tenant user and set up your continuous validation system. And plus PQC. That's a lot to do, yeah. So that's why I'm gonna introduce to you the solution we came up with. Because now we have to design systems that have multiple stakeholders. So we're gonna use physically unclonable function that was already mentioned in the talk before to generate security for all those applications. So what is a PUF? A physically unclonable function will create a root key here. So it will create a unique ID, a unique root key directly from the manufacturing process. So when you design with PUF, your wafer already has everything it needs for security directly on the bare die. And this is opposed to key injection. Key injection, you need an extra step to inject your root of trust. Yeah. Okay? So how do we use it to do everything we want? So we got our root key here. And then we're gonna need an extra true random number and a key derivation function to derive our super secret key into sub key. And each application, each link will have its own derived key, okay? So now the issue here is that you see, you rely all your trust on this key because there is a mathematical relation with everything here. So when you put all your eggs in the same basket, you need to make sure this key is not going to leak, this key is not going to be broken, and this key cannot be read. So we came up in the Shinshu labs, we came up with a new concept of making it dynamic, and we introduced the concept of dynamic PUF root of trust. Let's go back to what we want to do. So instead of designing a PUF that only creates one root key on power up or one-time root key, we're going to create a DNA on chip that can be constantly excited. So I can constantly regenerate random number. I constantly have one part static, one part random. And that allows me to remove that middleman of key derivation function and directly use each of my key from the root of trust for each application. Now, PQC is relatively new. So you can assume someone is going to make a mistake and you're going to have to renew a key. That's one of the reasons we build it dynamic, is because if you need to change one root key, you don't have to affect the other. And when you do this kind of system to deploy zero trust, to deploy post quantum, you can systematically build crypto-isolated channel. You guarantee true randomness directly from the semiconductor, and you can be power independent, which means if you have a server that can never be power off, I can still change my root of trust. I can still change my root key in case China invade. You shut down everything in one hexadecimal command. Yeah. So a typical use case besides zero trust and PQC on how you will use this kind of system in your device, you use one root key for each application. So secure boot, most likely not going to change. you have your company that gives you an update every year, so you keep it there. And then you have another company who will use your device and needs the storage. If you don't need to make those two companies talk to each other, because you do have multiple root keys that you manage. So you can just systematically derive this system for network storage and firmware update. So how does it translate into product and service? So we build IC, so silicon IP, and then we package them. So we call it silicon anchor secure, and then engine with not processor, P with a processor. We build module, key, and then we help you integrate directly in your system. Yeah. Okay. So each of our products, we go through certification. So for the source, we have entropy source, TRNG from the semiconductor with NIST and TRNG. For our chip, we have passed CSIP already. And the module and the key, they have FIDO certified integrated C. So now, how do we use it? So I finished, I have my PQC, I have my PUF, I have my algorithm. Now I need to go inside your living room. So when you end up having this key and the PUF equipped, now you can do authentication, you can sign, you can encrypt. So here, for example, you can recognize my 3 different root of trust. You can manage your storage with OneDrive. You can connect to Adobe and sign with a C2PA. And you can use your key for FIDO2 to connect to your Gmail. If you want to be more in company infrastructure, you can secure your NAS directly. You can build secure VPN. All of this with as much multiple root key as you want, because we provide you a means to create infinite root of trust with our PUF. Yeah. And what I promised you, the zero trust architecture. So in this case, everyone does different things. I don't know where you put your PDP, where you put your PEP, where you put your PA. So we can systematically attach module and key on each end of the network. Yeah. So this is real, it's over there. So here I put 1 color per root of trust. So we have a PQC demonstration here. We do a continuous challenge with a serial port. We do device ID, FIDO, and we use 2-factor authentication SSH. So, for example, here, so I have an edge device, and I'm going to use 3 different ID. 1 to make it unique, 1 to make the challenge, and 1 to do FIDO. Okay? So, is it here? Yeah. So I have a module here, and then I have my key. It's like the admin key or the access key plugged. And I will log into my camera. Then I end up behind the login page. So I plug my key. I pass the first challenge, which is the device ID. Then I switch to FIDO to make sure it's me. 1, 2, 3, 4, so I can remember my PIN. And then I touch to prove I'm human. There I access my stream. And in the back here, you're going to see a pass-fail, because every 10 seconds, we're going to do the challenge. And there I have like a double factor, end-to-end, and a continuous challenge for a directly zero trust application on an IP camera. Okay? If you want, I create another signature for C2PA. So C2PA is going to be a blockchain of your media. So I miss my hair. So I took a picture of myself. I start signing it. And then it's not very clear, but I added hair on the top. And then every time you edit a picture, you're going to record the manifest that will say who edit what. And that's a way to track where is your data from and to track how you can use it or not for AI. So we can give you more information in our booth about C2PA, but it's a similar standard as FIDO, and I think it's going to take over maybe next year. Adobe already use it, and OpenAI already use it. PQC, PQC is fast because we do hardware, so it's going to be very fast. So here we have key exchange. Well, that's it. There's not so much to do. So in PQC, we put it and we show it NIST in hardware, and then we do a key exchange. It's a bit sad, but we do a key exchange with ourselves. So this PQC engine needs a friend to talk to. Yeah. And the last one, we give you the means and API to build your own SDK and software. So if you're interested into building zero trust architecture with PUF, we can discuss over here. And there are many applications that we can do for military, we can do for communication, and we can do for daily life.